I will give a talk on Century of Light pioneered by Invisible Light as an introduction of our institute, so pLED. Go to background. The 21st century is often said to the century of light. This is because photonics devices such as laser, LED, and laser diode have been developed in 1960s. And then this technology became get matured and became available in low price. In fact, looking at our daily life, one can imagine one can no longer imagine a life without a light. Also, in the field of cutting-edge research, there are 10 Nobel Prizes related to light in the 21st century. So in this way, the light has a high potential and wide diversity. However, if the light is used so much in the field of daily life and cutting-edge research, one question comes to our mind. Light is already used up. But this is not true. So people may think of light as a visible light. However, the light is an electromagnetic wave covering a wide range of wavelengths from 0.1 to 5,000 micrometer. So the visible light is just part of it here. And the remaining part without the color is occupied by invisible light. Since invisible light has a unique light property different from visible light, new applications are expected. For example, the deep UV light can be used for activation of SARS-CoV-2 due to the strong damage to DNA and RNA. Infrared light can be used for breast health examination and blood glucose measurement using a spectral fingerprint of molecular vibration characteristic in infrared region. Also, the terahertz wave has attracted as a wireless carrier wave in next generation mobile communication 6G. In this way, the invisible light has a further possibility. However, these wavelength region of invisible light are still unexplored. Why? The reason is clear when comparing them with the visible light. So this invisible light lacks pieces of photonics devices such as LED or LD. So when considering a history of our university, so Tokushima University, highlighted by symbolic clock of blue LED like here, blue LED was born in Tokushima. Professor Shuji Nakamura is a great graduate of our university. So he graduated our university in 1979, and then he invented the blue LED using gallium nitride. Finally, he awarded the Nobel Prize in Physics 2014. Now, blue LED and following white LED is widely used in our daily life. Also, Nichiya Corporation is located at the south of Tokushima. Nichiya developed the world first blue LED in 1993 and world first white LED in 1996. Now, Nichiya is the world's largest supplier of LED. In this way, the Tokushima is a hot place of LED and related photonics, namely LED photonics. However, the LED or visible light is now technically matured, and it will be an era of low price competition. Unfortunately, it is difficult for Japan to win this competition because of too higher labor costs. So now, we have to find another or new direction of next generation LED. So one possible direction is to expand the wavelength of LED toward the invisible light region. So if so, the missing pieces of photonic devices in this wavelength region are filled by LED or LD, like here, social implementation of this application will rapidly promote in the same manner as the visible light region triggered by blue LED. So in this case, as a result, the invisible light is not an explored wavelength region, but reborn as a new wavelength region to create a new innovation. So we define the research investigating the use of the invisible light as a post-LED photonics. So the research field of post-LED photonics includes the developing source and pioneering application of visible light. Also, another important field of post-LED photonics is interdisciplinary research for medicine and photonics. So next slide shows the concept of the seamless photonic innovation that we are aiming for. Here, the creation of photonics innovation is linked to shooting a target with the arrow. And the horizontal axis indicates time development. So here, the arrow is corresponding to the practical photonics devices such as LED or LD, whereas the target is corresponding to application development. For example, in visible light region, the arrow of photonics devices are already developed. So now, the many arrows are just striking at the target of application related with the lighting and the display. But this target has still some space for the variable application. So one of the variable application is medical photonics, such as photodiagnostic, phototherapy of cancer, and photogenetics. On the other hand, in the invisible light region, now it is at the stage of making the arrow of photonics devices in the world. Importantly, if we can develop such an arrow of photonics devices prior to the rest of the world, we can monopolize the target without any arrow, namely blue ocean. More importantly, the timing at which the target appears is slightly different for each wavelength region. So, we can achieve the arrow of photonics devices prior to the world, so we can continuously create the photonic innovation by expanding the wavelength region to the deep UV, terahertz, and infrared region. In this way, the use of invisible light will lead to the seamless photonic innovation. So based on this concept, we founded the Institute of Post-LED Photonics, namely pLED, in 2019, and reorganized in 2022. So the present organization of the pLED is like here. So the Chief Executive Officer is Professor Takuya Sasaki, who is the University Research Director, and Chief Research Officer or CRO is me, so that Takeshi Yasui, and the Chief Marketing Officer or CMO is Dr. Kaoru Matsuoka. So the pLED is regarded as a special research zone in Tokushima University, including the independent PI for all staff, borderless organization, and research field to enhance borderless photonics and commercialization of research results. Now, so the pLED has three research departments. So fundamental photonics, next generation photonics, and interdisciplinary research for the medicine and photonics. Also, we invited the top-level researcher in Japan as a distinguished invited professor. So Professor Kaoru Minoshima in UEC University of Electrocommunications, and Dr. Takuo Tanaka in Riken, and Professor Tadao Nagatsuma in Osaka University. Furthermore, the management strategy office in which the head is Dr. Matsuoka helped the social implementation of research achievement in our institute. Okay, so let's move to the introduction of several topics in our institute. So the research useful in today's world is still countermeasures against COVID-19. Such countermeasures can be achieved by developing a therapeutic drug and vaccine together with the inactivation and detection of SARS-CoV-2. So the use of infrared light will be useful for the lower part of countermeasures. So the current inactivation of SARS-CoV-2 is performed by alcohol cleaning, but it takes time and effort. So use of the deep UV light enables the easy inactivation of SARS-CoV-2. Especially, so we are investigating to develop a recipe of inactivation for the SARS-CoV-2 based on the quantitative evaluation of inactivation power. So such an inactivation recipe will be useful as instruction to develop the several apparatus for the inactivation of SARS-CoV-2. Also, the current standard for testing of SARS-CoV-2 is a PCR. PCR benefit from high sensitivity by selective amplification of DNA or RNA, but it hampers the long testing time. So use of infrared light with plasmonics or optical comb enables rapid detection as well as high sensitivity detection. Okay, and okay, let's move to the research useful in the future. So the first topic is related with mobile wireless communication. So this slide shows the history of mobile wireless communications. So the technology evolution occurs every 10 years from 1G to 2G, like here, by increasing the wireless carrier frequency starting from 1.5 gigahertz. The present 5G use wireless carrier wave up to 28 gigahertz, so which is a millimeter wave and is within the range of electronics. However, so next 6G use a wireless carrier wave over 300 gigahertz, so which is a terahertz wave, so over the range of electronics. Now, so there are two technical challenges for 6G. So the first challenge is a technical limitation of wireless electronics. Until 5G, the wireless electronics are available. But the next 6G, such a wireless electronics may face the upper frequency limit or such as low signal quality and increased signal loss. So there is a considerable need for paradigm shift beyond the upper frequency limit of wireless electronics. So second technical challenge is the technical gap between optical and wireless communications. The present ICT is achieved by combination of optical communications by photonics and wireless communication based on the electronics. In this case, at the connecting point between optical and wireless communication, the signal conversion between optical signal and electric signal is required. So such a signal conversion result in some time delay. Until the 5G, such a time delay is negligible. However, the 6G requires ultra-low latency. So in this case, the time delay caused by signal conversion cannot be ignored. So the seamless connection between optical and wireless communication are strongly required. So these technical challenges arise from the use of electronics in wireless communication. So if we can achieve the 6G by photonics in place of electronics, these technical challenges will be overcome. So we define the 6G boosted by photonics such as microcom and photonic terahertz as photonic 6G, and we investigating the several research about them, like here. Okay, so the final topic is optical biosensor, which is a research useful in the future too. So now, we don't want to go to the hospital so much because of the risk of the COVID-19 infection. Also, increased medical cost due to the aging, a serious social issue in Japan. So now, we need the paradigm shift from therapeutic medicine to preventive medicine. So our institute, pLED, investigates post-LED photonics, including optical biosensor and 6G, as well as biomedical optics, such as inactivation and detection of SARS-CoV-2. Also, our university has a university hospital and Department of Medicine. So in which many researchers in biomarker, medical network, and big data, and AI. So if we combine these resources in our university into the optical biosensor, the sensing performance of the biosensor will be largely enhanced. So such a high performance optical biosensor enable or achieve the hospital in home. Such a home hospital enables the health management at host and collecting the big data of our health in cloud. And then every time the AI analyze our health condition. And then only when medical treatment is necessary, so the AI said to us to please go to the hospital. So such a home hospital accelerates the paradigm shift from therapeutic medicine to preventive medicine. So we consider the present COVID-19 crisis as a good turning point to do it. Okay, finally, recently, we start to contribute. Okay, anyway, until now, the pLED is contributing to the research activity of Tokushima University, but recently, we also start the contribution to the education. So transdisciplinary education program in medicine, photonics, and engineering. As explained before, the Tokushima reads the photonics and engineering. Also, Tokushima leads the medicine, so the university hospital and Department of Medicine actively research and education in this field. Also, Tokushima is a top runner of aged society in the Japan, like here. So, in other words, Tokushima is a super aging model prefecture in Japan. And so the right shows considering this fact, we set the vision of our university to contribute the creative super aging society. So which turns aging. This society it is a society that turns aging into a chance for happiness for all. So to this end, the interaction, understanding, and healthy, stress-free life is important. So we consider to achieve such a society, the photonics and medicine plays an important role. And to promote such a vision, so it is necessary to develop the transdisciplinary human resource. So now, so the pLED is start to educate and train the human resource with expertise in medicine, photonics, and engineering. So the one characteristics of this education program is a top-level scientists in Tokushima University engage the education, like here. And also the another characteristics of this program, education program, is a laboratory assignment start from the first year of bachelor course student. So in this way, the pLED contributes research and education for the photonic, post-LED photonics, and medical photonics. Okay, so finally we summarize my talk using this slide. So at the beginning of my talk, I said that the 21st century is a century of light. Until now, the main player in the century of light is, of course, visible light. But there are still 80 years in this century. So we have to find another or new main player or in century of light. So one promising candidate is invisible light. So I consider that the essence of the century of light is to use up the invisible light as well as the visible light and change the world. So such a post-LED photonics contributes the achievement of SDGs number 3, number 9, and number 11. Thank you for your kind attention.